us today for our ANLAB forum talk. And today I'm very pleased to introduce our speaker, Berthold Reinwald, who is actually one of our own here at Almaden. And I think a lot of you in the room know him. But for those of you who don't know him, I'll give a short introduction. Berthold is a principal research staff member and the technical lead for System ML. His current research areas include scalable analytics platforms and database technology. Berthold holds a PhD in computer science from the University of, I'm going to try to say this right, Erlangen, Nuremberg in Germany. Okay, I tried, okay. So, anyway. Okay.
That's good enough.
Okay, thank you.
All right, thanks, Michelle. Thank you, everyone, for coming. We are very pleased to be invited to present our research work here in this, at this venue. So I'm going to talk about scalable machine learning with System ML, and I can see that it is a very heterogeneous audience. So some of you guys may know what System ML is, some of you may never heard of it, and hopefully you're still interested in it. So we will just give a broad overview of what System ML is, explain to you why we designed it the way we did design it, but then also in order to add some spice to the presentation, we also, for very selected topics, we're going to dive into some detail to kind of show off a little bit how much innovation went into that project. Okay? So, I'm going to show a brief history of what System ML is. Has everyone seen the Star Wars movie over the holidays? Yes, Ron did. Okay. I tried to do a paper scroll like Star Wars at the beginning, but my PowerPoint skills were not good enough. So it's going to be a very boring animation here only. So if you scroll back a few years, Hadoop was there at some point in time, out of the blue. And it's a very powerful data parallel platform that allows you to do a lot of things. And IBM kind of went with Hadoop and wanted to bring it to the enterprise. And Hadoop supports many, many different workloads. And one very important workload is advanced analytics. And I'm using advanced analytics in a very broad sense here, but we looked at it mostly from machine learning perspective, especially predictive modeling and things like that. So if you're a data scientist, okay, and you are put in front of Hadoop, you would probably be very disgusted because it is really a step backwards in terms of consumability. It's doing, matrix multiplication at the assembler level. Okay, so there's a huge gap between advanced analytics and making it work on Hadoop. Okay, and that's when we said, well, this really calls for a system that allows you to develop scalable machine learning algorithms, and then you want to run those algorithms on a data parallel platform, such as MapReduce. That was in the past. These days we also support Spark, and we are looking into other data parallel frameworks as well. So we started off this effort about 6+ years ago as a research project, and we had quite a lot of accomplishments. And today, System ML, we have a compiler that allows to take those scalable machine learning algorithms and compile them down and run them on a data parallel platform. And we created a language for that allows you to express your machine learning algorithms. In order to show off the breadth of our language, we also proved out that we support a broad class of those scalable algorithms, and I'm going to take you through the list very shortly. As we went through the project, we did not come up with that idea on day one, but in the course of it, we worked very closely with customers, and we had several proofs of concept that helped us in directing that project quite nicely. We also had several research publications, and I'm going to show you a list in the course of the presentation as well as several disclosures. Okay, what is SystemML? Okay, in a nutshell, you can think of it, it gives you a language for the data scientist to implement your machine learning algorithms, and it comes with about 20 plus algorithms with the system. And SystemML, it's a compiler that takes those machine learning algorithms and compiles them down into a runtime. And we support several different execution modes. One of them, you can just run it as a Java application in a multi-threaded environment on a single node, or depending on your data characteristics and your system setup, we can also push it onto MapReduce or Spark. You can use SystemML in many different ways. You can embed it as a library in your solution. You can run it as a standalone Java application, or you can run it in a hybrid mode on the cluster, and we support various APIs that I will show you as well. Where is SystemML today? So it's been going on for quite a few years. SystemML, it's part of IBM's big data platform called IBM Big Insights 4.x. They have a module in there that is called the Data Scientist module, and part of this module is a SystemML compiler, and you can invoke the scalable algorithms in SystemML through a package called Big R in Big Insights. Then,
what does the R stand for, the big R? Research? Or?
No. You heard of this open source project called R? Yes, you did. So it's R MATLAB, so it's an open source statistical program, and we developed a package that is called Big R that you can load into your R interpreter, and then you can call out to Big Insights as well as SystemML. Okay. Since last year, we decided to open source SystemML. It's open source since August, and since October last year, it's an Apache incubation project. And here's a URL. I encourage you to go and check it out. We do that work together with STC, the Spark Technology Center in San Francisco, and they did a terrific job, really polishing SystemML, putting up the right documentation, then build environment, and so forth. And of course, it's also an ongoing research project here in Almaden.
How many people are actively working on SystemML in Almaden?
About a handful. Yep. And there's several people are here in the audience. Faraz is there, Nikita is there, Sasha is there. So there's the data scientist people as well as the systems people. Okay. Why should you care? What can you do with SystemML? Okay, so I pulled out this very old slide here actually, and from the discovered topics you can see we created this slide at a time when Tiger Woods was in trouble. Okay, we discovered that on Twitter and CNN. Anyways, so let me take you through that little scenario here. Let's assume you run a marketing campaign, you launch a new product, and you want to just see how well it's perceived in social media. So you connect to Twitter, and you download what people tweet about, okay? And then you want to analyze those tweets in order to find out what are the topics in a small number that people talk about on Twitter. Okay? So you can download all those tweets, and you can put them into this bag of words kind of model. Each tweet or document you represent in the form of a vector. Okay, in the columns are the tokens, and you end up with a very large matrix in terms of number of rows as well as number of tokens. That can be, number of rows can be millions, number of columns that could be tens of thousands or 100,000, and it's going to be a very sparse matrix. Okay. Now you can take that matrix and you can break it down into two lower ranked matrices, which is called matrix factorization. And those two lower rank matrices is going to be, one of the matrices is going to be a document matrix, and the other one is going to be the word matrix. Okay, and the common dimension is going to be K, which you can think of being the clusters. Okay, and if you do this matrix factorization, those topics here, you can then look at the word matrix, and per topic you can find out what words are being used in order to describe this topic, and you can come up with yet another algorithm that says, you know, what is the most important word to characterize the topic, and then you can eventually put it in a visualization like that. Okay. Now, in order to do this step, going from this very sparse V matrix and bring it down into two lower rank matrices, this is called matrix factorization, and the problem solution here really requires very large matrix factorization. The question is, how can you do that? Okay. Now, how would that look like in code? Okay. The code here is Scala code. Okay. And I'm only going to explain a part of this slide, so you have to really stay to the very end to see what's really happening. Okay. You cannot leave early. So first, we're going to connect to Twitter decahose. Okay. Just to get to the data source. And then we just register those tweets as a table, and then we just want to run some Spark SQL on those tweets. Okay, and you can, each tweet probably has around, let's say, 20 attributes, timestamp, author, names, and then eventually the body of the tweet itself. Okay, let's assume you want to do some exploration first, and you want to use Spark SQL for it. Then you would just type in some queries, and you look at the top 5 tweets, for instance, or you want to look at all the tweets and group them by language and count and so forth. And once you kind of select tweets that you're interested in, okay, then you go to the body of the tweets, okay, and hold on to them. Okay, that's a text. So now you end up with an array or RDD of strings. Okay. Now you want to take those tweets and you want to get to our very large sparse matrix. Okay. So for that, you need to have a featureizer that translates the tokens into counts and how many times this value showed up. So you get those feature vectors, let's call them that way. Okay. And those feature vectors, okay, you want to use and do the factorization on it. Okay. Now you need to have an algorithm that does the matrix factorization here. Okay, and that there are many different algorithms to do matrix factorization, and we settled on one that we found useful. It's called the Gaussian non-negative matrix factorization. Okay, and on this slide we don't see the implementation, but you will see it in the course of the presentation. But that will kind of be a scenario. You want to start off with the data source, you want to do some data exploration, and then you want to do some large-scale machine learning on it. In that case, your topic modeling, okay, and then you want to explore kind of your model itself and look at the results of it.
Just make sure I understand. So for each tweet, you just keep counting the number of words. The word tiger appeared 3 times, the word woods appeared twice. You don't care about adjacency like tiger woods.
Not
like
yet.
That. Just
no.
all you're counting is number of words.
Yes.
And each occurring of each word.
Yes, exactly.
Okay.
And you put them into those into this feature vector.
Trivial point on that. Are you looking at every single tweet, or are you looking at basically retweets where somebody, says
that is really up to you, and they kind of hide all of that in your initial exploration before you feed the text into our analysis. Okay. So you can select it by month, by year, by author, by whatever attributes may be there.
Okay, but for that slide before where you show what's important to the people in the U.S. at least, kind of how was that done? Was it every single tweet, or was it basically? I understand.
I think that was only the U.S. tweets.
Okay, fair enough.
And for some time span.
Yep.
Yes.
Did you also implement the matrix factorization itself?
Yes.
Okay.
Yes.
So you're not using existing libraries
No.
and extracting them?
No. My point is it's a very large-scale matrix factorization that you need to do here, and the existing libraries, they just didn't scale for that.
It's hard to believe that some library somewhere can't deal with big matrices.
Just one more question about
Yes.
what language did you use to write the factorization?
System okay?
Oh,
So
it's
it's
all
all
in the
in
system.
this little red circle here, so you have to stay for the rest of the presentation. Yes.
What feature generation methods are built in today, and can we inject our own features into the model?
You mean over here?
Yes.
That is really pre-system and model, so you can do whatever you want there.
Okay.
Okay. You can use whatever feature engineering works for your application.
Berthold?
Yes.
So at the beginning of each line, you have things like val and depth, so that's not R, right?
That is a Scala program.
What?
That's a Scala
Scala,
program.
sorry.
Yes. You could do a similar flow in Python, in Java. Okay, now matrix factorization in social media, that is only one possible use case, okay? And there are others, and as we talk to customers in the course of the time, we came across many different verticals. So we talked to insurance companies, we talked to car manufacturers, travel industry, financial services, and so forth. And I just want to highlight a couple of the use cases so that you don't think system and model, it's only about matrix factorization and social media. Not true at all. Okay? We try to be very broad and cover all the different industries. So just to give you some flavor of the possible use cases that we came across in the case of this insurance company here, they said, and it was a constructed example because they just wanted to test out our system in terms of scalability and performance. But they said, well, we have 1 million rows, okay, and we have about 95 columns. We want to select 15 out of the 95 and run linear regression on it, okay? And 15 out of 95, that's a very large number. If you do that sequentially, it's going to take a very long time for you. Okay, they asked us, how well can you parallelize that? Okay, and we did that. So that one is about being able to do, learn a large number of models in parallel, okay, and then score them accordingly. And you pick the best regression model that comes out of it. We were approached by an automotive company, and no, it did not have anything to do with emission control, so it's not that company. But it had to do with customer satisfaction. And they said, well, here's 2 million cars, and 8,000 of them, okay, were reacquired cars, also known as lemon cars, okay, which makes customers very unhappy. So it's about customer satisfaction, but it makes the company, the manufacturer, also very happy because it's very expensive. Okay, because they have to buy back those cars. And we were actually talking to we were approached by the guy who has to write a reacquired car check every month, and it was in the millions of dollars. So he was very motivated to find a solution to that problem. Okay, so they gave us a lot of data, so 10 million repair cases, 25 million parts exchanges, and so forth. And they wanted two things. Number one was, can you develop a classifier that says, is that car a lemon car or not? Okay. The model building here was actually not the hard part. The hard part was really the feature engineering because we did not really know which attributes to choose. Okay, so with a lot of help from them, okay, we kept on adding more and more features to our feature vectors, and eventually we ended up with 22,000 features per instance, which is a lot number, and that is the number after dummy coding. So let's be honest about it. Okay. So but we learned that the more features we added, the more precise our model got. Okay. And when we did the final presentations to the company, actually, they said on the phone, dealing with that number of features, they were not able to do with any other software before.
So how long did it take to even come up with that many features?
Month.
Can you give us an idea of some of the features had to do with something being a lemon?
With what?
With the car being a lemon, that's what you're interested in.
No,
So
that
what-
was the label, okay? You classified. The features had to do with diagnostic error codes. So if you have a modern car and you drive to the shop every, let's say, 3 months or so, they hook it up to all the devices and read out all kinds of sensor data. Okay? So they capture all that sensor data per car, okay, and that's what they gave us. Okay? So in the course of time, some red lights came on, captured with an error code or diagnostics code. Those are the features that we included in our feature
So
vectors.
still don't understand what they were trying to gain. So you're trying to decide based on what information whether a car is going to be a lemon, is
Yes.
a lemon. So So
Yes.
you'll tell us roughly what they found? I mean, I'm just trying to understand the kind of thing they could find that would be useful.
That's a good question, and
How did that save them money? I don't see that. I mean, all it did was,
no. So
it found lemons earlier. It didn't,
no,
it
exactly.
didn't get rid
Before
of
the
lemons.
car turns into a lemon car, so if it has certain symptoms,
Oh, but it's
okay, they take it, they fix it, okay, by changing some fluids or some pump or whatever combination might lead to a car turning into a lemon car.
Problems they have to buy it back and that's
Yes.
expensive.
Oh, see, that wasn't obvious. I was also wondering whether somebody is returning the car and then they are trying to decide
No,
whether
no,
the return
no.
car is really a lemon or not.
Yeah.
Okay, so we have many other use cases that we looked at. One from the travel industry. You're at an airport. They gave us a lot of Wi-Fi data. So if you go to the airport and you go through all the different floors and you connect to the Wi-Fi, they have the routers there, and they can triangulate actually as you connect very precisely, more or less, where you are in the airport. Okay, if they track that, then they can really find out and see how you go through the airport and how long you stay at different places. Okay, so they gave us around 60 million rows, which means like a timestamp as well as a position. So they took the entire airport floors, okay, and gridified it into 3 by 3 feet, okay, and then the MAC address to it, okay, which is a person. Not entirely true because everyone carries 2, 3, whatever devices what they shared, so it's not entirely true, but that's the gist of it. So they wanted us to develop some time series models here, and it was not just one ARIMA model, let's say, but many different models because there's many different people. Okay, so there's meeters, there's greeters, there's transit people, there's employees, and so forth. So they wanted us to kind of predict, or can we, predict at some time in the future at this grid here how many MAC addresses will be there. Okay, and then they can use that information to adjust personnel in the airport or do some duty-free advertisement. It was not clear to us what the precise use case is, but I think you get the gist of it.
This was which company again? What is that information?
It's an air transportation company, and I'm not going to tell you the name.
Oh, okay. Air transportation means something like American Airlines or
No, it was not an airline company. It was not an airline.
Okay.
And we had several other use cases. So, in the interest of time, let me briefly summarize here. Okay, if people talk about big data analytics, so the request that we kind of receive here and the takeaway here is you need to be able to compute a very large number of models. Okay, parallel model building is very important here. Obviously, big data, so you have a lot of rows in there, millions, billions of rows. You have a very large number of columns in there, not like the Iris data set where you have 5, 6 attributes, but it goes up to tens of thousands. Okay. Large data is sparse data, so your system implementation is better aware that the data is not dense, but it's sparse data, and you want to optimize for it. Okay. Large number of intermediates, that's a little hard to explain, so I'm going to skip that one. For correlation analysis, so if you have 10,000 attributes and you want to figure out whether your attributes are correlated, okay, then you have to look at a lot of pairs. Okay. You need to scale up that one. And people, yes, they very often they start off with some off-the-shelf algorithm, but as they learn about the data, as they learn about the accuracy, as they learn about their use case, they want to go in and tweak the algorithm. So custom analytics are very important. Off-the-shelf algorithms barely work. They're a starting point, but they're not the end game. Okay. So how do you do it? Okay. So if you go back to my Star Wars slide, at the bottom you have MapReduce or Spark. Things like Mahout just came out. All of it is useless from the data scientist point of view because they're used to R, they're used to MATLAB, they probably use SAS, maybe SPSS, and Python, scikit, those kind of packages. That's what the data scientists breathe, okay? But there's a big gap in between, okay? Now, as you implement your R code, you would have to worry about, well, will it scale? Will it parallelize? Okay. Will it run fast? Okay. Today I run on a gigabyte of data. and I put a lot of work in developing my algorithm, but hopefully my company is going to grow, my data set is going to grow, and 3 months from now I will have a terabyte of data. Will my same algorithm scale from 1 gigabyte to 1 terabyte? And I don't want to go back and redo my algorithm. Okay, so that's very important. So SystemML. Algorithms are expressed in our own language. It has an R-like syntax. Okay, and it's meant for the data scientists who are familiar with R, MATLAB, with those kind of concepts. Okay, and on the right-hand side we see one example, and we kind of we'll use that one as a running example going through it. You have, so you can develop your algorithm, and then we create APIs as well as language bindings. You can invoke those machine learning programs from Scala, from Java, from Python, from R, and so forth. Okay, and you can run them in very different execution modes, as a library, as a standalone Java application, MapReduce, Spark. Okay. The core of SystemML is our compiler. Okay, and we all understand what compilers are. Our differentiator is really our cost-based optimizer. Okay, which says, based on that machine learning program that I give you, and based on the data characteristics, today I run on a 1 gigabyte, tomorrow I have to run on a terabyte. Okay, based on those characteristics, I will generate execution plans. Okay, so a data scientist doesn't have to worry about should I run that operation as a mapper or as a reducer, how much data will get shuffled. That is all not important for the data scientist. For performance and scalability, it's extremely important. Okay? But leave that up to the SystemML compiler to figure out. That's what it's about. Okay? If you don't use SystemML, okay, and let me go back to the matrix factorization example, and there was a question earlier, will they ever see how the GNMF will work? If you use SystemML to implement GNMF, that's the entire matrix factorization algorithm. Okay. So it's not our algorithm, it's actually an algorithm that was developed by some AT&T folks 15 plus years ago. And it was a very interesting research paper that they published. And if you open up this publication, you will actually see those two update rules, and we more or less cut and paste them out and put them in our program. If you don't have SystemML, then you have to drop down to implementing Java MapReduce code, implement 6 or 8 MapReduce jobs with 1,500 lines of Java code. Okay. Big difference. The second point here is it's about data science. Okay, and once you run this algorithm, you look at the results, then you will come up with better ideas. And even for that one paper that the AT&T folks published, if you follow that trail of research, every other year a new paper came out with some improvement. Okay, and if you did it that way in your implementation, and you look at the improvements, then you can easily modify whatever implementation you have. If you didn't do it the SystemML way, then you would have to go back into your Java programs and modify and fiddle around to make it perform well again. Okay. So matrix factorization is not the only algorithm that we have in SystemML. We have many other ones. Here we try to cover a broad range of machine learning algorithms, and a lot of the algorithms are more or less started off with some textbook algorithm. Yes, sir?
So a question on the previous slide. So you said that your cost-based optimizer also takes inputs of the machine characteristics in your cluster. So I was wondering, what kind of characteristics do you include, and do you assume that the cluster is available completely to you, or you basically optimize the resources that you require and then ask the same from the...
Yes. Yes. So in order to get an answer to that question, you have to stay 20 more minutes in this presentation.
Man, you become a marketing.
I want to just keep my audience.
You should have withheld some of the food also.
You should say something about the chocolate.
Yeah, food is after the presentation.
You should say something about the chocolate at the end of the talk.
Chocolate, yes. Okay. So we have a lot of descriptive statistics functions in our language. Okay. And we have code to do univariate statistics on all your data, bivariate statistics where you have a lot of correlation analysis part of it. We have stratified bivariate statistics. We cover classification, with many different algorithms ranging from regression, logistic regression, SVMs, decision tree, random forest. You have one clustering algorithm, you're trying to add more regression algorithms, dimensional reduction. So I think you get the gist of it. There's quite some breadth here in terms of scalable algorithms that SystemML has already, but you also can implement your own custom algorithm. So they all come in DML source code. Okay, you are happy to take a look at it and modify them for your purposes. Yes.
Spark comes with machine learning, like some of the algorithms, some of these algorithms are implemented in MLlib. Did you do some performance comparison between MLlib and system and ML?
Yes. So MLlib is a library of machine learning algorithms implemented in Scala. Okay, so and Scala is a general purpose programming language. In our opinion, it's not meant for the data scientists. The data scientists, I believe, they are more interested in higher level languages such as or like syntax, as opposed to a general purpose machine learning language. Okay, so if you as a data scientist need to go in and modify an ML algorithm, you will have a hard time. Okay, because it's implemented in this general purpose language against the Spark core API. Okay, so that's number one. Number two is you ask the performance question, and that is a very, very difficult question to answer because matrix factorization, like the ALS algorithm, we have one implementation, and you're welcome to take a look at our implementation. They have an ALS implementation, okay? But if you look at the precise algorithm, they're not entirely comparable, okay? So they converge in different ways, okay? And some of them converge faster versus others, okay? So it's very difficult to just give you one number that says, SystemML is 1,000 times faster. I cannot say that. Okay? And it's also very data dependent. Okay, so for some data sets, this algorithm performs better, while for other data sets, another algorithm performs better. Okay? So that makes benchmarking extremely difficult. Okay? All right, so the top part of it is mostly model building kind of algorithms, but we also, for each one of the model building, we have the appropriate scoring script. Okay, so if you want to go and deploy your model, we have the scoring DML code for all those models here as well. We also have some data preparation functionality in SystemML that allows you to take, that allows you to point to a CSV file with character data in it, okay, and we kind of transform that data into numeric data, okay, by applying recoding, okay, by doing the dummy coding for categorical variables, binning, scaling, missing value imputation, those kind of things, which are very, very common in the data set that people want to run against. Okay. For some of the models, we also have PMML support. Okay, so everyone ready for some homework? Everyone is a data scientist now, okay? You guys are all super smart, okay? And you come up with a linear regression algorithm, okay? And I want to demonstrate to you how to do that using SystemML, okay? So open up your textbook. You want to do linear regression, so you have your X, your independent variables, and you have your dependent variables, your labels, okay, and you want to find the betas or the coefficients, okay. There's many. You can formulate that as an optimization problem here, and you want to minimize the difference there. And overnight, you had this grandiose idea to say, well, there's this cool method, and I'm going to call it conjugate gradient descent method. Okay. That's what you want to use to implement your linear regression algorithm. And in your dreams, you probably have seen those pictures here before. The way CG works is you choose a starting point, okay, and you choose a direction. And the step size, then you perform the step, end up somewhere. You adjust your direction, and you adjust your step size. hop again, and you keep on hopping until you're close to where you want to be, at which point you stop. Okay? So it's an iterative algorithm. Okay? So, and you want to run it against extremely large data. So on the right-hand side here, you see the SystemML implementation for it. Okay? You start off with a very cool initialization of the model by saying, all my betas are 0. Okay? So it's very primitive, so that's how you initialize it. Next, you compute the direction by using transpose X matrix multiplied with Y. So that's what you're going to use as an initial direction here. And it may be off a little bit from the center where you want to be. You settle on your convergence criteria, and then you get into your iterative algorithm, where you say, well, I have an initial direction. Let's compute a step size. And the step size is computed by using those matrix vector operations here. Okay? And then you update your initialization here, your x0, in order to get the x1 by using the step size and the direction. So you do w equals w plus over p. Okay? And then you figure out where you landed. Okay? You compute your new direction. Okay? And you look back. If you're close enough, then you stop. If not, then you do another step size, another update until you're converged. So that's how you would implement your cool CG algorithm. Okay? And once you're out of your loop, then you do some model analysis. You compute like the accuracy measures, some residuals, whatever you need in order to verify your model. But that's how you would work. The question now is, how do you run that? Okay? And in SystemML, we give you many different ways to invoke your CG implementation. Okay? As a starter, if you go to Apache and you download the jar file, we recommend like a command line kind of invocation. You can just invoke it, SystemML as a standalone application. You invoke your linear regression conjugate gradients DML script, and you point it to your X data, to your Y data, and where you want to store your betas. Okay. If you have a Spark cluster set up, okay, exactly the same DML script, you will compile to run against a Spark cluster or a MapReduce cluster. Okay, it's the same implementation, it doesn't matter to us. If you are like an R kind of guy, we also have an...
So you figure it out from the way you invoke this thing as to what environment it's running?
Yes, yes. So here we give you some utility shell script that says, run it against, compile it against the Spark backend, which also has a cluster information pointed to. Okay, so we know where to go to. If you're an R kind of guy, then you can use our Big R package. Okay, so from the comfort of your laptop, you bring up your RStudio or your Rattle or whatever tool you're familiar with. You connect to your cluster, and then you, through Big R package, you would just invoke your linear regression algorithm. Okay. If you are a solution developer or a tools kind of guy, then you would use our APIs. Okay. You can use our Java API, and you can try it out initially using the Spark shell, or you can use PySpark shell, depending on what language you're comfortable with, or you have a Java environment.
So if somebody has everything, how do you give them a cookbook to say under what condition which one you choose?
I have to repeat myself. You have to wait until the second to last slide. Then I can show you some performance numbers. Okay? And then you decide.
But that's extrapolatable from whatever you have done to some random situation?
No, because it depends on many different, it depends on...
So we don't have a tool or anything that they have to try it out and see.
Well, what do you want to see? Whether it runs faster on Spark versus MapReduce?
Something like that.
Because that's not the right question to ask, right?
I don't know. I mean, there could be any number of questions, I suppose.
Yes, exactly.
Criteria that you use to...
Yes. So we have our performance numbers, and that's what I will show.
Nice.
But there's other criteria as well.
Berthold?
Yes?
So in the work you've done so far, if you're interested in visualizing the output of your machine learning and kind of iterating with SystemML, what types of environments have you used so far?
So SystemML is like a core engine, okay? And so we don't have any visualization. The closest thing that I would recommend then is, if you're familiar with R, do it through R, and then you get all those
Does
visualizations.
Big Insights provide any tools or?
No, those come with open source R, so it was whatever ggplot or whatever they have in there, that's what you would use. Okay? But they're all kind of disconnected from the backend computation.
So there is no package to kind of go back and forth between visualizations and running stuff?
No,
you have
but
to
what you would do
design
here is you run your stuff, you get your coefficients out, you visualize the residuals.
Yeah, well, if you're doing it in R, you can
Yes.
use all of R's.
You can also do the same thing through notebooks, for instance. Okay, you can run it through the Scholar notebook, and then you get the notebook kind of visualizations there.
That's a Spark environment, right? The notebook.
No, notebook is not Spark. It can be used for Spark, but it can be used for many other things. Yes?
So what about other systems like Piano, Cafe, or TensorFlow? I mean,
Those are separate frameworks.
yeah.
Okay?
So,
And
I mean, those are specialized for machine learning algorithms.
those are specialized, even more specialized than just broader machine learning, but very often to just deep learning kind of scenarios.
So what would be the challenges for having system ML work with them?
Work with them or also do deep learning.
I mean, Spark is a very generic framework, so
Yes.
so is Hadoop, but these systems are not. They are specialized for machine learning. So, I mean, system ML, it's a compiler which compiles things to Hadoop or Hadoop or Spark framework, your algorithms and your queries. Then, how difficult is it to compile it down to the other frameworks?
Yes, well, the question is whether we want to compile down to those frameworks or we want to do in our native framework, which would be Spark or MapReduce, whatever computation is necessary to do something like Piano does. Okay. So a lot of those frameworks, they're very thin layers, and in terms of heavy computation, they just call out to GPUs in order to get the performance that they need. Okay, and we have similar efforts going on with SystemML here. Okay, if that one is sufficient, probably not. Okay, because that just gives you faster compute. If other things such as parameter servers or things like that are necessary, we don't have those yet, but we are looking into those. Okay, so here's the same script, okay, for conjugate gradient from a Scala environment, very similar to the way you've seen it before. The core of it here is you invoke your linear regression conjugate gradient DML script from a Scala program here. Again, the slide is partially to show off that SystemML plays very nicely with the Spark ecosystem. So before calling out to SystemML, you can do Spark SQL. You can even use some MLlib. I heard that comment here before. You have a whole bunch of data generators in there. You can just use those data generators, okay, to generate some random data sets. Okay, you do some Spark SQL processing on it to massage it, subset it, project, or whatever you need to do in order to get to your feature vectors. And then you can use whatever you came up with and feed it into SystemML, okay, to do the model building, okay, and then you get back into your Spark environment. You can look at your data frames, at your RDDs, at your coefficients, and eventually deploy them.
Is MATLAB also supported?
MATLAB, in what sense?
Like similar thing we can do in MATLAB or Octave?
We don't have a package to be called from MATLAB or Octave.
Okay.
No, we don't. We have only one for R. Okay. Spark came up before, so here's one more slide on Spark. They also have those pipelines there. So they have a pipeline API that kind of is to say, you want to point at some data, you want to massage the data, maybe run some SQL on it or do some tokenization on it and then do some model training on it. So very often you have those stages for feature engineering as well as model building that you are getting tired of invoking over and over again. So ML pipelines gives us this mechanism to define stages here. You can say here, I'm going to invoke that tokenizer, then I'm going to do some hashing on it to get to my feature vectors, and then I want to use logistic regression on it. Okay, and so you define that sequence of steps, okay, and call that pipeline. And then you can just invoke the pipeline, and under the covers it runs the workflow over and over again. Again, SystemML fits into this framework very nicely by saying, this logistic regression model, it's our SystemML logistic regression model that is just wrapped as an estimator to fit into that framework. Okay, now let's look a little bit behind the curtain. So far we talked about use cases, different scenarios. You all became data scientists, okay? You know how to invoke SystemML from the command line, from R, from Scala, from Java, whatever your environment is, okay? So why is SystemML great? Okay, what's really happening behind the curtain? Okay, so here's a high-level SystemML architecture slide. Okay, so you have your factorization script at the top, or your really cool conjugate gradient DML script. Okay, SystemML is a compiler. Okay, so we process the language, we have our compiler with the optimizer, and then we have our runtime. In terms of different backends, what we support is, we mentioned that before, we have we can run it as a Java application, okay, and still multi-threaded, okay, or you can run it on a cluster, which is a MapReduce Hadoop cluster or a Spark cluster. But the very important part here really is that SystemML does hybrid execution plans. Okay? So what does that mean? In your CG script, okay, for linear regression, there are, for very large operations on the X matrix, okay, if you have 1 billion rows in there and tens of thousands of columns, you have to do that in a distributed fashion, okay, for memory footprint and for performance, okay. But there's also a whole bunch of very small scale operations in there. There's no need to parallelize them. You will not gain anything out of it. So we always compile it down to hybrid execution plans. Okay? So the small operations run in a single node, while the expensive operations run on a cluster. Okay? So the picture here is a little bit misleading because we really do hybrid execution plans. Okay, one level deeper. Okay, so our language, it has an R-like syntax. We also have a Python-like syntax. It has a rich set of statistical functions in it. We support DML-bodied functions as well as external functions that you can call out to. Okay, and then it's a compiler, right? You do the syntax parsing. You break down the entire program into statement blocks and statements. We perform program analysis, type inference, dead code elimination, and many, many different things at that level. And eventually we construct what we call a hop DAG, and hops are high-level operators that represent the entire data flow in your entire program. Okay, and the nodes are our operations, and what we flow are either matrices or scalars. Okay, now at that level, you can perform optimizations. Optimizations are algebraic simplifications, some rewrite rules, okay, where you can just simplify, without changing the correctness, obviously. You can rewrite in order to get better performance. Okay? Then once you are happy with your hop DAG, then you translate that down into what we call low-level operators, which are the lock DAGs, and those are tied to the execution environment. So here we would say whether that thing will get executed in a single node or it will be done on MapReduce or on Spark. Okay, and then we have our runtime. Our runtime, we have this hybrid runtime. The core of our system is really a distributed matrix library, and the same block operations, okay, so we support blocked matrices. They run in single node as well as in distributed mode on partitions of the data. Okay? So it's one runtime that can be used in many different places, and that's very important for code maintenance. Okay? We have our CP, the control program, which is typically where we run the compiler, performs the optimization, generates the execution plan, and then it drives the operation. So it kicks off the spark or the MapReduce jobs accordingly. Okay. We spent a lot of time on numeric stability here because that's very important for very large operations. Our matrix library, it's very complex because it has to support several different formats, for dense formats as well as for sparse formats. And if you look into operations, then all of a sudden you have to worry about all the different combinations in order to take care of it. So you have to worry about dense times sparse, or sparse times sparse, or ultra sparse against ultra sparse, all those kind of different things. We also have a buffer pool in our CP with an eviction strategy there, and we have a recompiler. The recompiler is extremely important, and database guys, they know that as adaptive query processing. It's very important here for machine learning programs because in order to do our optimizations, we need to have some statistics, and we have very little statistics that we need only, like the number of rows, the number of columns, and the number of non-zero values if you have it. Okay? That's also important in order to do some semantic analysis on it. But if you have data-dependent operations, such as a computation of a contingency table in a DML program, then you would not know the size of the output. If you don't know the size of the output, then you cannot really optimize very well, and you have to make a worst-case assumption, which is, you have to do a distributed computation on it, okay? Which is probably not the right choice to make. Okay? But once, as we execute the ML program and we reach that point and we learn the dimension of that operations, then we can actually recompile the rest of the program. Okay? So in 2011, we published our first paper. Okay, it came up with the general concept as well as the MapReduce backend. In 2012, we had a paper that focuses on the descriptive statistics and the operations that we had to implement in our system in order to be numerically stable. In 2014, we worked with a team in Watson, and they developed a very custom algorithm to do what they call large-scale discriminative metric learning, which is similar to like a very specialized version of a KNN that you would compute. Okay, so those were kind of like our first users outside from our team. Okay. In 2014, we had a paper on task parallelism. So in our language, we have control structures such as loops and so forth, but we also have a very important control structure that is our powerful loop, where you can compute the instances, the body of each iteration in parallel, okay, because there is no loop carriage dependencies. And that is very important, and this powerful construct, as we call it, is used in about 60% of all our machine learning algorithms. Okay. In 2014, we had a paper on the system ML optimizer that explains the entire optimization chain that we have our system. We had a summer project on how to do distributed sampling, especially for meta learning. So if you have, if you want to do ensemble learning or cross validation, you may have to generate a very large number of samples. And how can you do that very efficiently? That's the paper. We also had a project last year, about or 2 years ago, about a GPU backend. Okay, our runtime operators, they would, not run on the CPU or whatever you have in there, but if appropriate, you would just call out to a cuPlus libraries and run also on a GPU, and you can get very significant performance benefits by doing that. We use the cuPlus libraries, but we also implemented our own, as we call them, suffused kernel. So we identified some patterns in our machine learning programs, and we realized that not just like blast level 4 kind of operations, but more complex operations that are very common in machine learning. We created a fused kernel for it that we just pushed onto the GPU, and it gave us very good performance benefits. Okay. We also had a paper on the resource elasticity. That question came up before. So that was the time when Yarn was introduced, or Mesos for that matter, and those infrastructures give us the ability to ask for an environment that you would like to have. Okay, so you can ask for container sizes, how many cores do you want to have in there, and so forth. The problem is, I don't know what to ask for. Okay, so what we implemented here is a kind of a pre-compiler that, given your data characteristics, given your machine learning program. It does a pre-analysis and kind of goes through the entire search space to figure out what configuration, system configuration would be best for executing your machine learning program. And that's what we settle on. That's what you can use as an information to go to your own resource manager and ask for the configuration. And it may or may not give it back to you. Okay. And we have more papers that I cannot talk about because they're double-blinded. All right. One paper that I want to point out a little bit more detail is on the system ML optimizer, because that is really the core of the system, and that is a big differentiator compared to many other platforms that are out there. The details are described in this paper. I just copied out this one slide just to give you some idea of what it all takes in order to optimize those machine learning programs. So on this slide, on the left-hand side, you see more or less the compilation chain that your program goes through. We do not do statement-by-statement compilation, so don't get misled here. We look at it holistically and at the entire program, but for PowerPoint purposes, it's just easier to show it that way. So you have an expression like that up there where you do x matrix multiplied with b plus sb multiplied with y. So you do like the syntax parsing on it. We do live variable analysis that tells you, how long do you have to hold on to your variables before you can remove them, or which ones go into a statement block and which ones come out at the end of it, so you can kind of clean up your buffer code and things like that. We also do semantic analysis there. So if you do a matrix multiplication, we need to make sure that the dimensions are really compatible, otherwise you just produce garbage. And then once you did the validate at the language level, you construct a hop stack. If you read it bottom up, you would say, well, you take in like the b vector here in the scalar, and you do a binary plus operation, then you do a matrix multiplication with x on it, and then you do a binary multiplication in order to get to the cube. Okay. The important thing that happens here is we annotate that DAG here with statistics. Okay. So we know the dimensions of B, so it has 500 rows and 1 column, so it's a vector. Okay. That one is a scalar, that one is a matrix, and those statistics we can use to do, and we understand our runtime implementation, we can use to do memory estimates. So we know exactly in order to do that operation, you need 12 kilobytes. In order to do that operation, you need 400 gigabytes. You need the left input, the right input, and the result, and maybe some intermediates. Now, depending on those annotations and the memory estimates, and you telling us what environment you're running in, so if your control program has only a 3 gigabyte JVM, okay, you cannot do that matrix multiplication in CP, okay, so you better do it in a distributed way. Right? But if you reconfigure your cluster, your environment, and all of a sudden you give me a terabyte of RAM, then I'll be happy to do it maybe that way, if it's beneficial. Okay, so this stack then, so we make the operator selection here, and then we compile it down into our lob stack here, which has more information in it, and eventually we generate a runtime program that we, in that case here, we execute against our Spark backend. Okay? So, does it matter? Yes, it matters a lot. Okay? So if I take your newly invented conjugate gradient algorithm here, and I run it against some data sets, okay? And we just run it against variable data sets. So we run it against 100 million rows, okay, in 10 columns, which translates to like 8 gigabytes, all the way from 10 columns to 10,000 columns, okay, which translates roughly to 8 terabytes here. Okay. So our system ML compiler knows that. It understands the data characteristics, and you also know it's kind of the environment that you need to run in order to get to your memory budgets there. Okay. So we do some analysis, and we just circuit here a couple of operations that we call the heavy operations in the script. So the rest of it doesn't really matter, but those are really the heavy operations that you really have to worry about and get right. Okay. Now, if you run the 8 gigabytes case, okay, that one fits into your driver memory. Okay, so you just do a multi-threaded execution of that entire program in the driver program, and you get your results, and you're happy. Okay. If you, instead of 10 columns, you have 100 columns, okay, it does not fit into the driver program anymore, so you have to bother Spark to do, let's say, distributed matrix multiplication. Okay? So in that case here, actually, before we go into the while loop, we put the data into RGBs and we cache it there in memory. Okay? And then if you do that, the vector size, okay, it fits into broadcast memory, so you can actually send it to all the executors in here. Okay? And we do have a fused operator in our runtime because we identified this TXXP as a very common pattern across many different machine learning programs. So we created a fused operator for it, and that's what we use in the distributed case. Okay, and that gives you very good performance. Now if we go to the next data size here, okay, then nothing changes except for the fact that the data does not fit into distributed aggregated memory anymore, and Spark will have to start spilling. Okay, and it does that very nicely for you. Okay. But we did not have to do a plan change here. If you go up to 8 terabytes with 10,000 columns, okay, then you cannot use our fused operator anymore because the vector doesn't fit anymore. Then we just do 2 subsequent matrix multiplication in a distributed way. Okay. So you should be happy with that because as a data scientist, how many lines of code did you have to change in your newly invented conjugate gradient script? 0. Okay. Thanks, Ron, for paying attention. I owe you a chocolate. Okay. What else? So performance matters. So this one is only system ML performance. Okay, and it's the same data characteristics that we just went through. Okay. On the x-axis, you see the different data sizes. Okay, and the y-axis is the execution time in log scale. Okay. Now we executed system ML. Those are all system ML runs, so there is no comparison. But we can run system ML in different modes, and that's what we want to highlight here. We run system ML against the Spark backend. We run system ML against the MapReduce backend, and then we also introduce this mode here where we say we do not run any operations in our driver, but we push all the operations onto Spark. Okay. That one here is important because we want to highlight that this single node execution for small operations will give you performance benefits for certain scenarios. Okay. Now, with 8 gigabytes, we decided to do only, our optimizer decided to do only a single node execution, and it pays off. It basically means those two numbers are more or less the same, right? Because no distributed operations have been executed. The 3 seconds are just variance. Doesn't matter. But if you push all the operations as distributed operations against a cluster compute, you will pay for it because the parallelization is not for free. Okay? But that optimization point is very important. The second point here is, if you look at those numbers, caching of data sets in distributed aggregate memory will give you performance benefits for iterative algorithms. Okay. So that's what bytes MapReduce here, because after each job, from iteration to iteration, you have to write out the data, read it back in. Write out, read it back in. However, in the case of Spark, you put it in the cache and you're fine. Okay? So that's why you see a performance difference here between Spark and MapReduce. Now, if you go up more, okay, 800 gigabytes, our distributed aggregate memory was about 300 gigabytes, so Spark starts to spill. Okay? But performance gap between MapReduce and Spark backends shrinks, okay, which is obvious. Right? And if you have extremely large data, like 8 terabytes, in that case, I would say you have too small of a cluster actually, so all your resources are fully utilized, and it doesn't really matter whether you use MapReduce or Spark, right? System ML is great, cost-based optimization is wonderful, and you need to have hybrid execution plan. So that's the takeaway. Okay, let me summarize. So System ML is a platform for scalable machine learning. The core of it SystemML is this cost-based optimizer. We have different modes, so the hybrid execution plans are very important. We understand different data characteristics, sparse data, dense data. You need to be able to process small number of columns and large number of columns, small number of rows, large number of rows, all that matters. Out of the box, we have a collection of algorithms that we took you through, and hopefully the list is growing. SystemML is open source now. You can always go and implement your own scalable machine learning algorithms there. That's all your own algorithms. And it's still an ongoing research project. We have a lot of things that we would like to add in terms of meta learning, improving that. Having this separation in SystemML, the way we architected it between the higher level and the lower levels, is very important to be. I'm not saying that Spark is the last framework that the community ever created. There's other frameworks there that people may want to exploit, such as Flink, for instance. And if your company decides to, not use Spark, but for whatever reasons, then you can more or less easily port it over, quote unquote. Okay, it's open source now. It's kind of a statement to IBM's commitment to open source. Questions? I'm out of chocolate.